Okay. I thought we had to educate this.
Okay, so this unit that we're starting today, exponential functions, is what we're looking at. It's going to end up, before we get done with it, being a combination of exponential functions and logarithmic functions. So you've seen that button on your calculator before that says log. So by the end of the unit, we'll get into what that means. Exponential functions and logarithmic functions, they're cousins. They go together, so that's why this unit is going to go together. Okay, so start off with some exponential growth and decay. You've got that labeled up there for me. My magic writer, see if it's going to work after it's been off a few days. Sure hope so.
I missed you.
Well, thank you. I missed you too. Alright, so let's draw an example of an exponential growth model and an exponential decay model and make some notes about them. Whoops, I don't like that one. Don't draw it like that. Let's try again. I don't like that. That's better. You got them already here? That's fabulous. Alright, so the one on the right, we've said a gazillion times in this class, we read a graph left to right just like you read a book. So the graph on the left where it says growth, if we were to jump on that thing left to right, you want it over here on your bicycle with me, if we jump on this thing left to right, we'd be going uphill. So it's an exponential growth model. If we jump on this one over here left to right, we'd be going downhill. So that's an exponential decay model. Exponential, that word means a couple of things. Exponent, so these equations are going to have a letter, a variable that's an exponent. It also means if something is exponential, grows exponential, or decays exponential, it grows fast. It's not like a steady linear slope. It explodes up. Most common type of word problem that I can think of off the top of my head for an exponential growth model is population explosions. There is always a population explosion question that comes up. Areas like our area, areas like Conway, those areas that are outside of Little Rock have experienced exponential growth over the years because people want to move out of Little Rock into the surrounding areas. So that population shoots way up. It grows a whole lot. Also, there's a common question where you're watching something under the microscope multiply. I can't remember, some kind of bacteria multiplies underneath the microscope exponentially. They split and grow and it's exponential. Most common decay problem, to go with that graph that I got over there on the right, there's several, but the most common decay and the project that will accompany this unit is about the value of a new car. If you've bought a new car lately, and Bradley's going to be sick of hearing about cars because that's what my first period class is talking about too. As soon as you pull that brand new car off of the parking lot, its value falls out the bottom. It drops drastically. So if you go and finance that car for 5 to 7 years, which is what most people do, by the time you pay it off in 5 to 7 years, you're paying way more than that car was ever worth. So its value decays exponentially. Okay? So there's some examples. Now with these little pictures that you've got drawn, we can label some stuff and get rolling with this. This, we called this one here, f of x is equal to b to the x. See how it's got an exponent that is a variable? It goes through that point there that I've got. It will always go through 0, 1. And then the other point that it will always go through is 1 and whatever your b is. So if this had been f of x equals 3 to the x, it would go through the point 1, 3.
So your x is always going to be 1 when you're graphing.
Well, that 1 will always be on the line somewhere, on the curve somewhere, yes. Okay, now another thing that the b right here will tell us, how if you don't have a picture of the graph, if that b is greater than 1, that means it's a growth. Okay? I think that tells us enough to get started on the growth. So over on the decay, this one, f of x is equal to b to the x, so it's the same thing. So it also goes through that point there, 0, 1, at its parent function. but then, and then it's going to go through 1b, just like the other one at its parent function. But this one, to tell it's a decay, it'll be less than 1, but it'll also have to be greater than 0. So what number is between 0 and 1? Okay, fractions or decimals, right? So anything that's a partial, so 3/4, 1/2, 7/8, those will tell you it's a decay, so it's going downhill. All right? Now, both of those parent functions that I've drawn there, and this might be a new word for some of us, both of those parent functions that I've drawn there have the x-axis as an asymptote. Woo, that was a $5 word, asymptote. So if I'm telling you this x-axis is an asymptote on these two, what could that mean? It's okay if you don't know, but you ought to be able to look at the graph and get a guess.
It always goes for that.
Okay, it looks like it's getting close to the x-axis. That's good, Grant. So same thing here. It looks like it's getting close to the x-axis. So by definition, asymptote is what it approaches but never touches. So it's going to get, like Grant said, it's going to it. It's going to get microscopically. We need a NASA microscope close to it, but it'll still never touch it. So a lot of times on our calculator, it'll look like it touches it, but you know, I've told you before, our calculators are not HD, 2080, S, whatever all those initials are. They're pretty bad resolution. So even though it looks like it might touch it, it really doesn't. Okay? So it approaches it, but never touches it. Now, its parent function, it's the x-axis. But just like every function that we've done in here, we're going to be able to move these things around. So they'll have an asymptote, but it just might not always be the x-axis. Might be down here at y equals -3 or something like that. All right. Hang in there, Riley. You're going to be all right.
I know about it.
I do. I do. All right. So before we graph it, or we will graph it, but before we do, first off, is this an exponential function? Yes, because it's got a variable that's an exponent. Okay, everybody with me on that? So since it's an exponential function, we ought to be able to figure out if it's going to be a growth or a decay. Grant's right. How does he know it's going to be a growth? 2's bigger than 1.
That's a 2?
Mm-hmm.
Oh, I thought it was a Z.
I've always put a line through my Z's.
Oh, my bad.
So 2's bigger than 1, so it's going to be a growth. So we know already then a couple of points that this thing's going to go through. See if I can grab a piece of graph paper without the world coming to an end. Maybe. There we go. We know it's going to go through what 2 points?
0, 1.
0, 1. And 1, 2. Where'd that 1, 2 come from?
2B.
1B. Very good. So I know it's a growth. I know 2 points it's going to go through. Now, looking at those 2 points that we got there, we have to be a little bit smarter than the average bear. We're not just going to connect those in a line. Since this is an exponential function, we know it's going to make one of those curves that approaches but does not touch the x-axis. So we can draw the curve, the graph of that now. Okay, I know it's growth, so it's going to start low. It's going to be down here on the x-axis, and then bam, it's going to explode up. So get something looking like that. Now, just like every function that we've done, your calculator can graph that. So grab your calculator, get y equals, and let's put that in there and see if I got close. Y equals 2, and then you remember that little top button is your power button. Woohoo! And guess what? You can even go to your table and find some more of those points on there if you need more points, right?
Oh gosh.
Pretty good stuff. Pretty easy, huh?
It's a month ago.
Your axes went away.
So just as close?
Let's see here.
Yep, that's correct.
Axes off, it says. Someone turn axes on. See what that does for it. Hey!
On what?
Alright, everybody okay on that? Alright. Let's keep this up here. And let's look at this one. Y equals 1/2 to the x. Now don't type it in your calculator yet. Don't type it in your calculator yet. Everybody with me? Shh.
Yes, ma'am.
Y equals 1/2 to the x. Is it an exponential function?
Yes.
Yes, yes, yes. Good job. Is it a growth or a decay?
Decay.
Decay. Very good, because it's got a fraction. So left to right, it's going to drop, like the bottom's going to fall out before it levels off. So do I know 2 points that might go through? 0, 1. So it's going to share that point. 1 and 1/2. Right?
So it always starts at 0, 1.
0, 1 when it has not been moved. How do we know these two have not been moved? That they're the basic parents. Very good. There's nothing in, Garrett, that's a fabulous question. There's nothing extra on here being added or subtracted or anything, so it's still at the origin. If we start putting a +7 on here, it won't, we'll have to move it, but we're not there to yet today. Alright, so this is going to come through, hit those points, and then level off on the asymptote. That would be 1, 1/2. Because our B was 1/2. Okay, when we get it drawn, check it in your calculator. See how we did. Say what, sister? Good. You can go through your table and find some more points. I want to talk about a few more of those points in your table this time. You got it in there, so you can go to your table and tell me some answers. When x is -3, what does your table say y is?
8.
When x is -2.
4.
When x is -1.
2.
0. 1.
That's sweet.
1.
Yeah. I'll do it.
1 is 1/2.
Thank you. 2.
1/4.
1/4. Okay, so let's talk about what these y's tell us. Okay, over here at -3, 1, 2, 3, it was all the way up at 8. But then it came down half to -4, and then half to 2. And the reason they're halving is because that number is a half. But what do you notice the farther it goes on the x-axis?
They get smaller and smaller.
They're never gonna hit 0. So if we did 1/2 of this, it would be 1/8. And then it would be 1/16th, and then 1/32nd, and then 1/64th, which is going to be so small, my eyes can't see it. But it's still not 0. So it gets close, 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 but it doesn't get it.
And then 256.
1/256. Like, who can see that?
So
Nobody.
it's like an infinite number of fractions.
Yes. Yes. Cool stuff, cool stuff.
It's sleeping, Miss Wright.
That's what I heard there, Garrett. That's what I heard.
Keeping you
You're from a
informed.
student or from sleep.
We have school, guys. Go home and nap.
I have no idea what the next one will be.
Usually, Garrett, and you know, I'm wrong once a year, but usually once you get here, the odds of you going home are not very likely. Usually. Because it's more dangerous to send you home now than just to wait until it all turns to rain and melts away.
It will never melt away.
But
Yeah.
if
You
it's
got a
just
point.
going to keep getting worse.
It's supposed to turn to rain around lunchtime.
She's got
I'm
a,
just,
she's got a point.
But I'm gonna
Because
die
rain
at
won't make it
lunchtime.
This thing.
That and also screw school. Well, actually, I want to stay here. I love what I can just do.
If it isn't it, if it's under freezing, the rain will just turn into ice.
Exactly.
Yeah.
Boom. And we'll
Which I don't know. I don't know if it's freezing, but
I'm pretty sure it's actually going up.
so technically, if it's freezing, rain will make it even worse.
Is it there like an eye?
if it's freezing, yeah. You're
What's
right.
the temperature?
But
If it's
that's
freezing,
not what
Somewhere at 32 right now.
33. What's it feel like?
the feel like doesn't matter.
Yeah.
Oh,
28.
Doesn't matter what it feels like.
so if it stays under 33, it should freeze.
Okay, look at these two things. Shh. Look at these two things. I got on the left y equals a times 1 plus r to the t power. Got
that's
a Garrett.
t,
Then on
not
the
a pi.
right, y equals a times 1 minus r to the t power. So
Move the points.
these are, you're right, these are still exponential models because they still got an exponent that's a variable. We got a t up there, but there's stuff going on. So they're going to be moved around. They're not going to necessarily be at the origin anymore. One of these is a growth and one of them is a decay, and common sense will tell you which one you think is which. Okay, if we add something, we're growing. If we take something away, we're decaying. Very good, very good. Any other,
Do you have to graph it if you already know what it
yeah, you'll still be asked to graph. But it's not difficult.
is? So can you have any letter as your like exponent? Whatever?
Yes,
Okay.
yes.
The exponent letter doesn't matter though, does it?
Correct. Correct. The T, the probably the reason T is chosen here is a lot of the formulas that we're going to see that are real life formulas are our banking formulas or investment formulas, money type deals. And so that T usually represents the time that you put the money in, the investment time. Alright, so that was just an example of a thing. I want to do a real life problem with you now. Let me see. Let me make sure I don't need to add anything else to those before we go away. Oh, we're good. Alright. So let's say now the value of a car Y, in thousands of dollars can be approximated by the model Y equals 25 times 0.85 to the T power, where T is the number of years since the car was new. Alright, so a few things, and this is that page that I just went away from. That wasn't for no reason. This actually relates to that page. So, first off, do you think this is a growth or a decay? Alright, let me tell you, Tori is correct that this is a decay, but I need you to know why.
Because it's the 0.85.
Okay, look back at the decay one that we just wrote down. Right? Didn't we just write that down? So, what is in this place?
The
0.85. So this is a decay, and I did tell you this was about a car's value. So the car's value usually does depreciate. How much is it depreciating a year? Not 85%. Say that again. Not 85 cents. Not $85. Okay? It's not 85 anything. 1 minus what got that 85? Ding, ding, ding. Okay, see where we're headed now? So what would my rate be? Huh? Close.
24?
1 minus what is 0.85? 15%, right? So our R, because it 1 minus what had to equal 0.85? 1 minus 0.15 equals, that's a,
Oh.
so our depreciation rate is 15%. So that car's losing 15% of its value every year. Okay? So that told us what we were dealing with there. Now, what about the A? What is the A telling us? This is a real life problem about buying a car. Do I need to read you the problem again?
That's your multiplying 15% times 25.
Yeah, but why 25? What is the 25?
That's how much it costs.
Okay, that's the original value of the car. So who buys a $25 car? So remember when I read this here? The value of the car Y in thousands.
It should be 25,000.
So the original cost of the car was $25,000. Okay, so we now know where all of this came from that previous screen. We're buying a car that's $25,000. It's going down in value 15% a year. So what could I do with this T to figure out how much my car will be worth every year? No. You're wanting to do way more work than me, Landy Joe. Let's keep it simple.
1, 2, 3, 4.
How would I figure out how much my car's going to be worth in 2 years after I bought it?
Oh, you let
Plug
it
it in.
Put a 2 in for the T. What would I do to figure out how much my car will be worth 5 years after I bought it? Put a 5 in for the T. Okay? Could I let my calculator do some work there so I don't have to do that?
Yes.
What would I do? Okay, hit y equals. Go to your y equals like you're going to graph it. 25. Type it just like it is, but instead of a T, put the X. Y equals 25, parentheses, 0.85. Close your parentheses to the T. Now the negatives, when you go to your table, that's where you're going to need to be. The negatives are going to be useless because you don't have a negative amount of years, right?
Wow.
So when I first bought the car, year 0, what do you?
25.
25. It was worth what it was worth, 25,000. 1 year later, how much is it worth?
21.25.
25.
21 point what?
Wait,
Two
what
pop.
Wait, it's 21.25.
Next.
18.063.
Okay, so after just 1 year, it's already lost almost $4,000 of its value. Okay, that's what your table is seeing. After 2 years, what's my car worth?
18.1.
Okay, after, let's jump down, let's say we kept it 10 years.
4.5.
So after 10 years, the car that I paid $25,000 for is barely worth $5,000. That car lost its value pretty
And most of
fast,
the
didn't
time,
it?
like, you don't keep it in that good of shape, so it goes
Yeah.
down a lot more.
Right,
than
so you're not even going to get that when you try to sell it or trade it.
Is this how people like actually see it out on?
Yeah, and you're going to have a project over it at the end of the unit. Cool stuff, cool stuff. Alrighty. Make out what we need there. Alright, in 2000, so 20 years ago, in 2000, the world population was about 6.09 billion. Just for you, Bradley, we're leaving cars for a minute. In the year 2000, the world population was that. During the next 13 years, the world population increased by 1.18% each year. So we started off with 6.09 billion. For the next 13 years, we're gaining 1.18% a year. Part A says write an exponential growth model to represent this. So what you would look at, exponential growth, is that model. Right? Okay with that? All right. So A is based on the last problem you learned, you figured out that A is what you're starting with. So in this case, what's our population starting? 6.09 billion. So I'm going to say Y equals 6.09. And now I got to have a 1 plus, what's my rate?
1.18.
1.18%. How do I write that as a decimal?
0.118.
Nope.
No, wait.
Come on, this is a middle school question. How do you write 1.18% as a decimal?
1.18%. Would it be 0.0118?
Yes, you move it twice. Very good, Mr. Witherspoon. So 0.0118 to the T. Now, that's an okay equation, but there's one piece of that that you can now simplify.
You can just go ahead and add the 1.
Uh-huh. So we would write that as and so you've written an equation for the world's population growth from the years 2000 to 2013. So you could now plug that into the y equals on your calculator. 0, when you went to look at your table, 0 would mean the year 2000, right? 1 would mean the year 2001, 2 would mean the year 2002. So you could tell what the population for each of those years is. Now, what I need you to realize is we've not done any difficult math. But if you don't know what we're plugging into and the steps we're taking, this is probably not something you're going to be able to guess your way up on, right? So you need to have this stuff in your notes and know that was the starting amount, that was the rate, know where this stuff's coming from. So at 5 years, that'd be the year 2005. What would the world's population be?
6.4579.
So about 6.46 billion.
So this is a growth?
Mm-hmm. Everybody good with that one? Ready to try another one? Whoop whoop. We're getting there. Y'all doing good?
Oh.
I don't know.
So the average growth.
Yes. Yes. So the percentage here is greater than 100, so it's 1 point something. On that car one, it was less than 100, right? Alrighty. Let me throw you a common one that you're going to need in your notes. This says A equals P times 1 plus, you're going to need this, R over N to the NT power. Okay, you're going to need that. This is what they call the compound interest formula. Now, you've worked in Algebra 1, and if we haven't already done it in here, you'll work with what's called a simple interest formula. Simple interest is just I equals PR to the T. It's a lot more simple. This compounded interest, what this means, compounded interest is just how the bank calculates your interest. Like the simple interest, it's yearly. They do it once a year, that's it. Compounded, they could do it quarterly. They could calculate your interest 4 times a year. They could do it semi-annually, twice a year. They could do it monthly, 12 times a year. So you've got different variables that come into play on that. Okay, so here's the problem that we'll dissect this with. It says you deposit $9,000 in an account. All right, so I'm going to push pause. Look at those variables up there. Which variable do you think is going to represent the $9,000 I deposited in my account? Yes, very good, Chloe. The P. The P would be in the same place as that A was earlier, wouldn't it? And the A stood for what we started with, right? P in this case, this banker's formula as I call it, P stands for principal. Principal is how much you put down or what you invest or what you start with. So if we invest $9,000, our P is $9,000. Okay? Everybody all right on that? Okay, so let me continue my reading now. You deposit $9,000 in an account that pays 1.46% annual interest. Okay, so look up there at what we got. What do you think the 1.46% would go in? We've already got the P taken care of. So you think it's going to be the A, the R, or the N, or the T? Okay, R, interest rate. So I would rewrite my interest rate here as a decimal by move my decimal point 2 times. So my R would be 0.0146. Right? Okay? Alright, so we've got the P, we've got the R. We know from our previous problem T will be time in years. So the only things left that we don't know about yet are the A and the N. The A, that's just going to be the final amount that you have after you've made this investment. The N is the tricky part. The N is how often your bank is figuring this interest, how often they're compounding it. And that's all based on the wording. So listen as I read it again. You deposit $9,000 in an account that pays 1.46% annual interest. Find the balance after 3 years if the interest is compounded quarterly. There was the key word, quarterly. Quarterly means 4 times a year. So your N is 4, quarterly. Okay, everybody got that? Different words tell you different clues for your N. Now, I skipped over it quick when I was reading it, but it says find the balance after 3 years. So your T will be 3 for this particular problem. So we say A equals, starting with $9,000. 1's always 1 plus 0.0146 divided by 4 to the 4 times 3 power. Now you don't want to be in the y equals now. You're just working on your normal add, subtract, multiply, divide screen because you've done all this stuff. You've given them $9,000. You've sat back and waited 3 years. Now how much money's in your account? So you're just looking for that answer. All right, Grant got $9,402.21, and that's correct. So keep practicing if you didn't get that because you need to be able to get it. Sometimes I get overwhelmed on typing all this in the calculator, so if you had trouble, you might want to break it down. You know, do this first, then add 1 to it, then do it to the 12th power, then multiply it by 9,000, break it down into smaller parts if you need to. Use common sense. You started with $9,000. Your interest rate is barely above 1. So you're not expecting to become a billionaire in these 3 years, right? It's a little bit more than we started with. So that makes good common sense. If I had done all this work and come up with $8 billion after 3 years and only a 1% interest rate, I might know I screwed up. If I'd done all this work and came up with less than I started, I'd know I screwed up, right? Use common sense on that real world type problem. Good, good, good. And you could plug anything you wanted, any year you wanted in for the T. I just asked for 3. That's why you plugged the 3 in. All right, what do you think about growth and decay?
Down.
It's not very hard, and it's actually real world type stuff, so it's pretty cool to me. Good, good, good. Next lesson, what we add to this tomorrow, this is going to make some of you uneasy. It's the number, did you catch that? It's the number E. E is a number.
Oh yeah, that.
Woohoo! It's a lot like pi. It's an irrational number that means it keeps going forever.
Numbers should only be real.
No. Your calculator uses an E on scientific notation instead of a times 10. It's something different. Alright, so that'll be tomorrow. And we got to get that E covered because that comes into play when we start talking about logs. Logs and E go together.
Yeah, well, I got it.